This is Mercedes López-Morales. Thank you for listening to this talk. In this presentation, I will give you an overview of what we have learned so far about the interiors and atmospheres of small planets from the measurements of their masses and radii. Since you might be watching this recording in the future, I wanted to clarify that what I'm presenting here is based on the knowledge that we had on this topic at the end of 2020. During this talk, I will walk you through the following points. First, what do we mean when we talk about small exoplanets? Then, I will explain to you why we are so interested in them. In the third part of the talk, I will show you how does the observational mass-radius relation look like from the observations that we have collected so far. And then, I will show you what we have found so far about the interiors and atmospheres of small exoplanets from those mass and radius observations. Finally, I will go into some of the main remaining questions on this topic. So without any further delay, let's jump into the first question. What do people working on exoplanets mean when they say small planet? Well, in some contexts, we might be referring to rocky planets like Earth. But typically, when we say small planets, we refer to this peak in the size distribution of exoplanets discovered by the Kepler mission satellite last decade. With the Kepler mission, we discovered that about 78% of the planets in our galaxy have sizes smaller than 4 times the size of Earth. So the majority of exoplanets in the galaxy are smaller than Uranus and Neptune. The largest peak that you see here in the histogram corresponds to planets with radii around 2 Earth radii. These are the so-called super-Earths. Super-Earths are the single most common type of planet in the galaxy, but as you all well know, we don't have any super-Earths in the solar system. And this makes super-Earths conceptually completely unknown worlds to us. We don't know anything about their properties. Obviously, just the fact that we don't know anything about small exoplanets makes them interesting already. But here I highlight some of the specific reasons for why we think that small exoplanets are so interesting. The first reason is trying to understand the big picture of planetary formation and evolution. Why are most planets smaller than 4 Earth radii? Why is there a peak at 2 Earth radii? Why are there no super-Earths in the solar system? And is the distribution of planets that we observe a result of their formation or their evolution? A second reason why we are interested is understanding the properties of these planets. What are their interiors made of? What are their atmospheres made of? And finally, a third reason that drives us towards these small planets and trying to understand them is what are the properties of rocky planets? How diverse is the population of rocky planets in the galaxy? How common is Earth? We don't have answers yet for many of these questions. So our work in the next 1 or 2 decades will be to try to answer these questions by studying a large number of planets over a wide range of parameter space so we can do population studies. In a sense, the study of exoplanets is at a similar stage as stellar astrophysics was 100 years ago, and that is exciting. Trying to summarize the work currently underway on all these questions takes much longer than the 1-hour slot that I have for this talk. So in the remaining of the talk, I will present to you where we are today in this point number 2, understanding the properties of the interiors and atmospheres of small planets. And I will do this by using what we have learned so far from the observed mass-radius relation. As you probably already know, we consider the mass and radius of planets as their most fundamental parameters. From the mass and radius of a planet, we can derive their density, and from that density, we can model their interior structure, so we can tell if the planet has a solid core or not. From its mass and radius, we can also tell if a planet has an atmosphere. The radii of many small planets has been measured so far with spaceborne missions such as Kepler, K2, and TESS. Measuring their masses is currently the bottleneck for progress in this field. All the mass measurements of small planets so far come from radial velocity surveys and from transit time invariation measurements. For your reference, I list here some of the radial velocity instruments that we are using to measure precise masses of a small planet. I also summarize here the current precision mass measurements from transit time invariation, where there are a total of 17 measurements, 12 from Kepler planets, and 5 from the 7-planet system TRAPPIST-1. In total, we have to date about 30 small planets with mass measurements with precisions better than 10%, and about 90 mass measurements with precision measurements of better than 20%. To give you an idea of what these precision levels mean, you should know that to differentiate between different interior composition models, we need to measure the mass of the planet with a precision better than 10%. And a precision of about 20% is enough to robustly characterize the planet's atmosphere. So if we plot those 90 mass measurements of exoplanets for Earth radii and smaller, for which we have mass measurements with precision of 20% or better, this is how their mass radius diagram looks like. The circles in the diagram correspond to mass measurements via radial velocities, and the triangles correspond to transit time invariation mass measurements. Notice the TRAPPIST planets that are shown as the triangles in the bottom right corner of the plot, since they all have masses and radii similar to Earth. Notice also the different color lines across the diagram. Each of these lines shows a different planetary interior composition model. Red is for planets with a pure iron interior. Orange is for planets with an interior composition of about 1/3 iron and 2/3 magnesium silicates. And the two greenish models correspond to planets with interiors composed of 50 to 100% water. The symbols are also color-coded as a function of the planet temperature, but please ignore that for now, since we are going to focus on the location of all these measurements in the diagram and the different composition models. For guidance, we also show in the gray circles the location of Uranus and Neptune on the bottom right, and Venus and Earth on the top left. Also for guidance, I will highlight any planet along the orange line model or below that model, since those will be rocky planets with small secondary atmospheres like Earth. Planets along the green lines will have cores made out of rock and volatiles, mainly water, and a significant primordial atmosphere. And planets above those lines will contain lighter volatiles, such as hydrogen and helium in their atmospheres, and those atmospheres are also expected to be primordial. So with this data, we can now start providing some answers to some of the questions about the interiors and atmospheres of small exoplanets. In particular, we can start providing answers to the 4 following questions, which I will focus on for the remaining of the talk. So here are those questions. First, how massive can a planet be and still be rocky? By rocky, we mean a planet with a composition dominated by magnesium silicate rocks and iron, and only a thin secondary atmosphere. Theoretically, we think that we already know what the answer is, and that is that planets more massive than about 10 Earth masses accrete a significant envelope, but we don't know if the observations agree. The second question is, how low in mass can a planet be and still accrete and retain a substantial primordial hydrogen and helium envelope? The third question is there a unique mass radius relation? And the fourth question is if the mass-radius relation of these small planets is not unique, what is the number distribution of rocky versus icy versus gaseous planets? Let's look into each one of these questions in more detail with the current data. Let's look into the first question. How massive can a rocky planet be? To answer that question, we need to focus on this part of the mass-radius relation. As I said before, our definition of a rocky planet is a planet with an interior composition dominated by magnesium silicate rock and iron, and only a thin secondary atmosphere, something like Earth. As I also said before, theoretically we think that we also know the answer, and that is that planets more massive than 10 Earth masses accrete a significant envelope. But until now, we did not have the observations to test that theoretical prediction. So, with the observations that we have so far, if you focus on the models inside the highlighted area, you can see that there are planets with masses up to 10 Earth masses, up like all the way on the orange line. So those appear to be rocky. For higher masses, there appears to be no planets that fall along that orange line or under it, but there are larger planets that fall above that line. This means that there are planets with a solid interior made out mostly of magnesium silicate, but they also must contain a significant amount of water envelopes. This is neat because it appears to confirm theoretical predictions. That is, that the critical mass that a planetary core can accrete is about 10 Earth masses, and once they reach that critical mass, if the gas in the disk from where the planet is forming still has not evaporated, the planetary core will undergo a runaway growth phase until it clears up all the gas surrounding it, and it produces a gap in the disk. That planet then appears as a gas giant. Let's move now to question number 2. How low mass a planet can retain a hydrogen-helium envelope? To answer that question, here is the same observational mass-radius relation I was showing you before, but now I only show planets with measurements coming from radial velocities. The planets with masses measured via transit time variations have been removed. This gray area is where we expect to find planets with a significant hydrogen and helium envelope. So based on the radial velocity data alone, there seems to be a physical transition around 6 Earth masses and about 1.6 to 1.7 Earth radii between planets with just bare cores and very, very thin atmospheres, and planets which can retain large hydrogen and helium envelopes. Planets with lower masses are bare cores, while planets with more masses than 6 Earth masses can either be bare cores or accrete and retain large envelopes. But this is what happens when we put back in the diagram the planets with masses measured via transit timing variations. The 6 Earth mass divide is not as clear anymore, and instead there seems to be lower mass planets which have managed to accrete and retain large hydrogen and helium envelopes. How is this happening? There is already some work done related to this particular question by, for example, Becky Dawson and collaborators. And in that work, they look into how planets in multiple systems could manage to accrete significant envelopes. Very, very low mass planets might be able to accrete and retain significant hydrogen and helium envelopes under certain circumstances, such as, for example, if they form in multiple planet systems, which is precisely the type of systems in which transit timing variation observations are possible. The idea is that multiple planet systems are formed in more massive disks with a lot more material available, and that allows for 1, a larger number of cores to form in the system, and 2, it also allows for more material to be still around for those cores to accrete. This is a hypothesis. We don't have a solid answer yet, but it could explain why small planets in multiple systems appear to be more likely to retain significant envelopes. Another piece of information for this currently unsolved puzzle is that multiple planet systems are preferably found around metal poor stars, as opposed to radial velocity small planets, which are found across a wide range of metallicities. This is another hint suggesting somewhat different formation environments between planets in multiple systems and planets not in multiple systems. Finally, observationally, we have started to search for what we call the superpuffs, which would be planets in this upper left region of the mass radius diagram to establish better observational constraints on mass. Okay, so let's move now to question number 3. The third question we can try to answer with the current observational mass radius relation of small planets is whether that mass radius relation is unique. To put these questions into a broader context, this figure shows the observational mass radius relation for celestial objects from stars like the Sun on the top right to solar system moons and dwarf planets on the bottom left. Over the years, there has been attempts to derive analytical expressions for a mass radius relation that covers this entire mass range. And here I show you one of those attempts by Chen and Kip in 2015. They do a fairly nice job fitting this entire mass radius relation using 4 different analytical expressions that you can see in this plot as the blue-grayish lines. Notice that for solar system moons and dwarf planets, which is what they call in the plot Terran worlds, and for stars, the fits look fairly good, but not so much for planets between about 2 Earth masses and for brown dwarfs, where you see that there is a lot more scatter. With that red square in the middle of the plot, I highlighted the mass radius parameter space for small planets that we are considering in this plot. There is a lot of scatter in that region, as you can see. And if we zoom in, you can see the mass radius relation that I have shown you before. When we zoom in, the scatter becomes even more apparent. So I think the conclusion that we can derive at this point is that no, the mass radius relation of small planets is by no means unique, and there must be other parameters responsible for the observed distribution of masses and radii for these planets. What those other parameters are is still pretty much an open question, but some ideas include environmental parameters such as stellar irradiation levels or the presence of other planets in the system, stellar parameters such as the mass, age, or metallicity of the host star, and other factors that we are currently not taking into account. So this is one of the questions where I think that theorists or modelers are going to be working on for a while, but I will show you in some of the next slides some of the progress that is being made in this front. Before I do that, let's go into question number 4. This fourth and last question is about demographics. By the numbers, what fraction of small planets are rocky, icy, or gaseous? Before showing you where we are in our attempt to answer this last question, let me quickly remind you each definition. First, we have rocky planets. A rocky planet is a planet with a solid core and with a thin secondary atmosphere, meaning that if the planet initially had a larger atmosphere, it accreted most of it during formation, which is what we call a primordial atmosphere, but that atmosphere got lost by photoevaporation or via other mechanisms, and it got replaced by a secondary atmosphere that could have been formed, for example, via outgassing of the interior layers of the planet, or so on. By definition, the interiors of these planets, as I mentioned earlier, are mostly composed of magnesium and silicate rocks and metals such as iron, and the atmospheres have high molecular weight. The second type of planets are icy planets. Icy planets also have solid cores, but in this case, the core has a significant amount of ices. That is water, methane, ammonia. Their atmospheres are expected to be hydrogen dominated. Neptune and Uranus, for example, are suggested to be icy giants. The atmospheres of icy giants can be a mix of the originally accreted gas during formation and outgassing. And finally, we have what we call the gaseous planets. They have very low abundance of rocks or other solid materials, so they most likely don't have a solid core, and they have a thick primary atmosphere dominated by hydrogen and helium. So the question again is, what fraction of those small planets are in each one of these groups? This question is important because it tells us about how small planets form and evolve, and it also gives us an idea of how many rocky, potentially terrestrial planets we would expect to find. So let's try to answer this question by going back to the observed mass-radius relation so far. The first thing that jumps out in this plot is the fact that most planets appear in two clusters located, one around the 33% interior iron rocky planet model, and the other one around the water-rich interior models. There also appears to be a gap in between those two clusters. That gap, which appears now clearly in the mass-radius relation also, was already discovered by Fulton et al. In 2017 and was reported in their paper as the radius gap. Fulton et al. Discovered this radius gap using refined planet radius observations from Kepler. They basically went through all the small planet candidates found by the Kepler mission, refined the radius measurements by refining the parameters of the host stars via careful analysis of their spectra and new parallaxes. And that is how they got this clean detection of a valley in between these two peaks. This result was obtained only using radius measurements with no masses available for the majority of the planets in the sample. So it is cool to see that the gap now also shows up in the mass-radius relation. A parallel analysis by Li Zheng, also in 2017, also discovered that radius gap and suggested that the location of the gap moves from about 1.3 Earth radii for planets around low-mass M dwarfs to 2.2 Earth radii for planets around solar-type stars. The conclusion of the presence of a gap from Li Zheng's papers was not as clear as the Fulton result, because Zheng used the radii of the Kepler planets as reported. So the error bars were larger and the results were more blurred because of not having as well determined stellar parameters. Nonetheless, the detection of the gap seems to be there. Zheng's work was also the first one to suggest that the presence of a drift in radius for the location of the gap depending on the stellar mass. Although the drift is fairly clearly seen for the G dwarfs to the early M dwarfs, as you can see in this plot, the number statistics for late M dwarfs were poor at the time, and it is hard to tell whether there really is a gap in there. The problem with the Kepler targets is that they're mostly located outside the galactic plane, and therefore the Kepler sample contains very few late M dwarfs. But Cloutier and Minois 2019 made some nice progress in that front in a more recent study by adding planets around late M dwarfs discovered by K2. In this more recent study, Cloutier and Minois 2019 combined again like Kepler and K2 planets, and they confirmed the trend in the location of the radius gap observed by Zheng in 2017 between G-type stars and early M dwarfs. But they don't find a gap in the radius distribution of planets around late M dwarfs. This result suggests that small planets among the smallest stars form with gas-poor envelopes, maybe because of this, that these stars form from don't have a lot of gas. The radius gap is the first feature in the mass-radius relation that jumps at us. But let's go back to the observed mass-radius diagram to highlight another interesting feature in the distribution of planets. If you look at the distribution of planets in the diagram, it seems that most observed planets with radii between about 2 and 3 Earth radii have masses between about 5 and 20 Earth masses. Then, there appears to be a gap in radius between about 3 and 4 Earth radii, and most of the observed planets about 4 Earth radii or larger have higher masses. That second gap in the mass-radius relation has been referred to as the radius cliff. So let's now go into the possible explanations for all these characteristics of small planet demographics observed so far in the mass-radius diagram. Why the radius gap? Why the radius cliff? And why the concentration of planets between 2 and 3.5 Earth radii? Let's start with the radius cliff. There have been several attempts to explain that sudden drop in the number of planets around 3.5 Earth radii. But the leading explanation at the moment is what is called fugacity crisis, suggested by Kite et al. In 2019. In this scenario, the authors assume that planets with radii of about 3 Earth radii still have molten cores because of the slow interior cooling from formation due to the very thick atmosphere that they have, in which heat from the interior cannot easily dissipate. Therefore, the bottom of the planet's atmosphere is in direct contact with a magma ocean. That, combined with the fact that atmospheric pressures are higher than 1 gigapascal in the atmosphere interior boundary. 2, the planet's atmosphere has a significant amount of primordial hydrogen. And 3, the solubility of hydrogen into magma at high pressures. Those 3 characteristics combined creates a scenario in which the hydrogen in the planet's atmosphere can dissolve into the magma, and the radius of the planet does not increase in that case. The authors of this work theorize that this would be the scenario for planets with an atmosphere to core mass ratio of about 20% by weight. And for smaller planets, planets with smaller than that value atmosphere to core mass ratios, we would end up with super Earth and rocky planets. And for higher atmosphere to core mass ratios values, we would end up with gas giants because of atmospheric accretion right away. This figure from the Kite et al. 2019 paper illustrates how, in their simulation, they can reproduce the large gap in planet occurrence at around 3 Earth radii when including this hydrogen fugacity effect, versus the distribution that they would obtain if they did not include the fugacity crisis effect. The paper also includes some observational predictions that could be tested in the future. For example, if the fugacity crisis theory is true, the location and radius of that radius cliff would not depend on the mass of the host star or the lifetime of the formation disk, since this would be just an ongoing equilibrium process in the interior of the planet. Another observational prediction is that because of the difference in solubility of the different elements, some of them would dissolve in the magma and some others wouldn't. So the elemental ratio in the planet atmosphere would be significantly different from the elemental ratio in the host star. Let's now move to potential explanations for the radius gap. There are currently 3 main proposed mechanisms to explain why the radius gap exists and why does its location change as a function of host star mass. These theories are photoevaporation, core power mass loss, and water-rich versus water-poor formation. In the case of photoevaporation, the idea is that the majority of small planets form with a gas-rich envelope, and that envelope gets eroded over time by high-energy radiation from the host star. If that is the case, we should see some correlations in our observations. First, we should see a correlation between the planet radius and their orbital distance from the host star, in which planets of a given mass have larger radii as they sit farther away from the host star. We should also see a correlation between the planet radius and the host star mass for planets of a certain mass at a certain distance from the host star. The planets around low mass stars should have smaller radii because low mass stars emit larger amounts of high energy photons. And finally, we should see a correlation with the planet radius and the age of the system, in which planets orbiting around older stars should be smaller in radii. Photoevaporation is currently the preferred theory for the formation of the radius gap. The second proposed mechanism is core power mass loss. The idea in this case is that heat from the cooling core of the planet can blow away all or part of its outer atmospheric layers. How much atmosphere the planet is able to keep depends on whether the heat capacity, as you see here as C, of the atmosphere is higher than the heat capacity of the core or not. If the heat capacity of the core is higher than the heat capacity of the atmosphere, then all the atmosphere gets blown away and the planet ends up looking like a bare core with no atmosphere. On the other hand, if the heat capacity of the atmosphere is higher than the heat capacity of the core, then the planet will retain at least a portion of its primordial atmosphere and it will appear larger in size. Like in the case of photoevaporation, if core power mass loss is responsible for the radius gap, one would expect to also see some observational correlations. In this case, and like in the case of photoevaporation, we would see no correlation between the radius of the planet and their orbital period. There also would be no correlation between the radius of the planet and the high energy irradiation from the host star. Instead, the correlation would be with the bolometric flux of the star, which would make the planet core hotter as they formed. And finally, like in the case of photoevaporation, there might be a correlation with the age of the system, with planets in older systems having had more time to lose their envelopes as their interiors cooled down, and then those would look smaller than younger planets. Finally, let's look into a potential explanation for the observed distribution of planets between about 2 and 4 Earth radii. As you see again in the mass radius diagram, most of the observed small planets are in this radius range, and their measured masses range from about 5 to 20 Earth masses. The current hypothesis is that planets either have a rocky core surrounded by hydrogen and helium gaseous envelopes, in which case these planets would be called gas dwarfs, or they contain a significant amount of multi-component water-dominated ices or fluids, in which case the planets would be called water worlds. As you can see in the diagram, planets in the mass range between about 10 and 15 Earth masses, most of them appear to be about half ice and half rock by mass, and half radii of 2.5 Earth radius, which matches the second peak of the radius bimodal distribution that produces the radius gap. Any planet in the 2 to 4 Earth radius range requires a gas envelope of at most a few percent in mass, regardless of the core composition. In 2019, Zheng et al. Produced planet growth models where they make the planet formation environment either water-rich or water-poor. And those models reproduce the radius gap and the accumulation of planets at around 2.5 Earth radii. So Zheng et al. Suggested that, one, statistically, most planets with radii between 2 and 4 Earth radii are actually water worlds. And two, they also suggested that the radius gap is a product of formation and not evolution. In their model, planets below the gap would have formed in water-poor environments, and planets above the gap would have formed in water-rich environments. This theory actually has the problem that it does not predict a potential correlation with orbital distance, which is something that we are already starting to see hints of a correlation like that in the observations. But this theory does predict the lack of a gap for planets around the smallest stars detected by Cloutier and Menoir 2019. So this is more or less where we are today on this topic of trying to understand the interiors and atmospheres of small planets. As you can see, we're just starting to understand their properties, and there's still a lot of work to do, but we already have some answers, or at least some good clues about the questions that we asked. Here, to wrap up the talk, I will give you a summary of the 4 questions that we posed, and the answers or ideas about potential answers that we have so far. So to the first question, how massive can a rocky planet be? The answer is that the maximum mass of a rocky planet appears to be about 10 Earth masses. More massive planets will accrete significant envelopes. To the second question, how low mass a planet can retain a hydrogen-helium envelope? The answer appears to be 6 Earth masses, unless the planet is part of a multi-planet system, in which case it appears that even less massive planets can sustain significant envelopes. To the third question, is the mass-radius relation of small planets unique? The answer is no. The value of those 2 parameters for a given planet depends on formation and evolution parameters of the system, such as the stellar parameters, the composition of the disk that the planet formed in, or irradiation levels on the planet, and other parameters that we might not be considering. And finally, the current answer to the last question, what determines the observed distribution of rocky, icy, or gaseous planets, is that we need more observations to answer that question properly, but some clues are starting to emerge. For example, there is a gap in the radius distribution of planets, and the exact location of the gap appears to depend on the mass or spectral type of the host star. The gap in radius also appears to disappear for planets around the smallest stars, that is, M dwarfs with masses about 4 Earth sun masses. And finally, there also appears to be a radius cliff at around 3 Earth radii, which could be possibly explained by the atmosphere of the planet dissolving into a liquid magma interior. So this is where we are today on this topic. Hopefully in the next few years, with more observations, we will have a clearer understanding of how these planets form and evolve. But all we can do for now is to continue collecting data on these targets. Thank you for listening.